Hello everyone, I am Brigadier Mishra, a PhD student at IIT Bombay. So this is the online session of elements of solar energy conversion, and this is week 10. So for this week there was one lecture on the CPC, paraboloid dish and central receiver tower, and from the next lecture the photovoltaic studies has started. Okay, so for this session I am covering that CPC and central receiver tower portion, and the remaining portion will be covered by another TA, Mr. Pawan, in tomorrow's session. Okay, so I have taken three questions for this session. Okay, that is belong to CPC and central receiver tower. We will try to solve these questions. I have picked these questions from Sukhatme and Nayak book, so you can check. Okay, so first one is an untruncated CPC has a half acceptance angle of 36 degree and an absorber width of 10 centimeter. Calculate the concentration ratio, the aperture, the height and the surface area of the concentrator per meter length. So if I can draw a CPC, okay, so it looks like this two parabolas, and then we have a linear absorber, line absorber I can say, or line receiver. Okay, so these are two parabolas, and these 2 points. So this is the aperture of width W, this is the height H, and here is the receiver. Okay, so this length is B, and the acceptance angle, okay, the acceptance angle is 2 theta A. So for this case it is given that the half of acceptance angle is 36 degree. That means theta A equals to 18 degree. Okay, and absorber width 10 centimeter, that is B equals to 10 centimeter, and we have to calculate concentration ratio, aperture, height and the surface. That means we need CW and surface area of the concentrator per meter length, that means A con by L. Okay, so these three things we need to calculate based on the data given for this untruncated CPC. Okay, untruncated means it is not truncated, or means it is not cut down, or the size has not been reduced for this CPC. Okay, because literature shows that the outer part is not much help to increase the temperature of the absorber. That means it doesn't involve much to concentrate the incident beam radiation to the receiver. Okay, so that is why there are studies to truncate the CPC with very little sacrificing the efficiency. That will help to reduce the cost of the CPC. Okay, so we are not looking into that. So first thing is the concentration ratio. So as you know that it is directly proportional to 1 by sine of acceptance angle. So here sorry, this is half of acceptance angle, so it is theta equals to 36 degree. Okay, so C equals to 1 by sine theta A, or I can say 1 by sine 36 degree. So concentration ratio is given, this is equals to 1.7. Now another way to calculate concentration ratio is C equals to W by B, where W is the aperture width and B is the absorber width. Okay, and since we already know it is equals to 1.7, so we can calculate W, and W is nothing but 1.7 into B, and B is given as 10 centimeter, so it is 17 centimeter. Okay, so we got the W, and now we have to calculate the height. Okay, so the formula of the ratio of height and width of the CPC can be calculated using concentration ratio. So it is 1 plus C into 1 minus 1 by C square to the power half. So H, if you can put all the values, it is 17 into half, 1 plus 1.7, 1 minus 1.7 square to the power half, and if you solve this you will get 18.559 centimeter, which is around 18.6 centimeter. Okay, or 18.56 centimeter you can say. So this is the height, and now we need to calculate the surface area of the concentrator per meter length. Okay, so surface area of the concentrator is denoted as a con, and per unit length means L. Okay, so there is a formula that A concentration area of concentration by WL equals to sine theta A 1 plus sine theta A cos theta A by sine square theta A plus natural logarithm 1 plus sine theta A into 1 plus cos theta A divided by sine theta A into cos theta A plus 2 plus 2 sine theta A to the power half. Okay, and minus root 2 cos theta A by 1 plus sine theta A to the power 3 by 2. So also if you remember from the lecture that if C is greater than 3, greater than 3, then we can write A con by WL equals to 1 plus C. Okay, but for this case, since here C is 1.7, so we cannot use this formula, we need to use this one. Okay, so if you put all the values, then you will get A concentration by W into L equals to so it is 0.933 into 2.342 plus 0.635 minus 0.572, and then taking W here this side, which into yeah. So now A concentration by L equals to 38.14 38.14 centimeter. Now if so if I take L equals to 1 meter square, then A concentration will be 0.3814 meter square. Okay, so this is the area of concentration, surface area of the concentrator. So this was the question for to calculate the geometry and concentration ratio of a given CPC with half acceptance angle and absorber width. Okay, so we have calculated concentration ratio, the height of the CPC, and the area of concentrator. Okay, so in this next question we will do the thermal analysis of a CPC. Okay, so this is again from Sukhatme and Nayak book. So a CPC is mounted on a horizontal east-west axis and oriented with its aperture plane sloping at an angle of 40 degree. So beta is given as 40 degree. The concentration ratio of the collector is 6.5. So C is also given. The width of the absorber plate is 6 centimeter, that means B is given 6 centimeter, and its length is 2 meter, that means L is also given. The collector is used for heating a fluid. So Cp of fluid is 2.35 kilojoule per kilogram Kelvin, and then the inlet temperature is given TFI equals to 130 degree centigrade. So calculate the exit temperature of the fluid. So we need to calculate TFO and the instantaneous collection efficiency and eta. Okay, for the following situation. So the location of collector is New Delhi, date is November 5, time is 11 hour. Here Ig and Id is given. We can write it like 735 watt per meter square, and this is 162 watt per meter square. Okay, and all the tube outer diameter, this is DO, this is DI, transmissivity of glass cover tau, reflectivity of concentrator rho, and absorptivity of the surface alpha, overall loss coefficient UL, heat transfer coefficient HF, and mass flow rate m dot, ambient temperature TA. Everything is given. Okay, so we need to so how we should proceed. Okay, so so first we need to calculate the geometry of CPC. Okay, so we have this concentration ratio here, so we can calculate the acceptance angle. Okay, so so C equals to 1 by sin theta I. Okay, and since we already know C, so we can calculate theta equals to sine inverse 1 by C, and this is 1 by 6.5. so if you solve this, you will get theta A equals to 8.85 degree. That means the acceptance angle, that is 2 theta is 17.70 degree. Okay, so this will be the acceptance angle, and now we need to calculate the A concentration by WL. Now if you can see earlier, here we used this expression since C was less than 3 for this case, but we have also mentioned that if C is greater than 3, this ratio can easily calculated by this formula, simply 1 plus C. So here if you see, C is greater than 3, it is 6.5. so we don't need to use that complicated formula. We can easily calculate A concentration by WL is 1 plus C, and this is 1 plus 6.5, that means 7.5. okay, so okay, now So we already have L is given as 2. Okay, so we can calculate A concentration by W equals to 7.5 into 2, and this will be 15. Now another way to calculate C is here. So C is 1 by sine theta, and this is also equals to W by B, we mentioned earlier, and B is already given 6 centimeter, so we can calculate W here again. So W is B into C. Okay, so B is in centimeter, so we want it in meters, so it is 0.06 into 6.5, so it will be 0.39 meter. Okay, so now we can calculate the concentration area, or the area of concentrator. Okay, equals to 15 into 0.39 meter square, as L is given in the meter. Okay, so it will be just use calculator. So 15 into 0.39, it is 5.85. okay, so 5.85 meter square. Now we also need to calculate the multiple reflection, like in CPC rays can go with the multiple reflections before reaching to the receiver or the absorber plate. So we can calculate the number of times a beam undergo multiple reflection before reaching to the receiver. So that is denoted by M, and the formula to calculate is 1 by 2 sine theta A con by WL minus 1 minus sine theta A 1 plus 2 sine theta A by 2 sine square theta A. Okay, so if you put all the values, 1 by 2 sine 8.85, and we have already calculated this A con by WL is 7.5, so it is 7.5 minus, you can also check, this can be a good exercise, that you can use this these values, put the acceptance angle value here, okay, to calculate A con by WL, and you will find that both are very near. This is simply 1 plus C, that is 7.5, and if you put sine theta value here, you will get around 7.52 or 53. Okay, so both are nearly equal. That is why this is the approximation, that is this 1 plus C when C is greater than 3. Okay, so 7 to 7.5 minus 1 minus sine 8.85, 1 plus 2 sine 8.85 divided by 2 sine square 8.85. So if you solve this, you will get 1.00027. So we assume it 1. So that means almost all the radiation beam hitting the coming inside the absorber plate, inside the CPC, hitting the surface just after one reflection. Okay, so it is not going to multiple reflections. That is why it is equals to 1. So now we need to calculate the fluxes. Okay, so whatever the flux is incident, total flux, that means the beam radiation as well as diffuse radiation coming to the absorber plate. So we need to calculate the fluxes. Now in order to calculate fluxes, we again need to calculate those angles, declination angle. So here uh, time is given 11 hour, LAT is given. Okay, so first we need to calculate n. So it is November 5. Okay, so for November 5, n equals to 309. Okay, then you can calculate delta 23.45 sine 360 by 365 and plus 24. Okay, so if you put all the values, you will get minus 16.55 degree. Okay, and now if you calculate omega, since here it is given local apparent time, we can directly use this time to calculate omega. Okay, so because if it is given in Indian Standard Time IST, then we have to use the correction time formula to get the LAT, and then we have calculated omega, since omega is with respect to the local solar noon, not the standard solar noon. Okay, so omega is time minus 12 into 15, and it is 11 hours. 11 minus 12 into 15, so it is minus 15 degree. Okay, minus since it is before the noon, that means in the morning. Okay, so if you not remember, it is negative since time is before noon. Okay, so we have omega and we have delta here calculated. Now we can, and we also have beta, which is 40 degree, and the latitude. Okay, latitude is given, this is L, so latitude is 28.58 degree north. L is 28.58 degree north. So we can calculate, so if you know the useful formula for the useful radiation, S is equals to IB/RB plus IT by C tau rho E alpha. Okay, so this is the formula. We have already given tau alpha. What is rho E? Rho is the effective reflectivity of the concentrator. So rho is rho to the power m, where rho is the reflectivity of the mirror or reflected surface, and m we have already calculated here, m equals to 1. So since m equals to 1, we have already calculated rho equals to rho. Okay, now we need to so all the quantities are known here, only unknown quantity is this RB, which is the tilt factor. Okay, so tilt factor RB is so I'm writing the values, so it is sine minus 16.55 degree, sine, if you remember, this is sine L minus beta, so it is 28.58 degree minus 40, as 40 is the beta of the CPC, plus cos minus 16.55 degree cos minus 15 degree, this is cos omega, okay, into cos 28.58 degree minus 40 degree divided by sine 28.58 degree sine minus 16.55 degree plus cos 28.58 degree cos minus 16.55 degree and into again cos minus 15 degree. If you remember, we had discussed that in some textbooks omega is considered positive in the morning and negative in the afternoon, okay, but that doesn't change the value of this tilt factor as omega comes with cos, and cos minus theta is cos theta. So either we take positive or negative value here, it doesn't change the RB, okay. So if you put all the values, you will get RB equals to 1.4243. so now we can calculate S as IBRB plus ID by C tau rho to the power m by alpha. So and IB, we have given IG and ID, so we can calculate IB by simply subtracting both the values, 735 minus 162 into 1.4243, and ID is here 162 by concentration ratio 6.5, okay, into transmissivity is given here. So yeah, tau is 0.89, rho is 0.87, and absorptivity of absorber surface is 0.94. so after putting all these value here, this 0.89 into 0.87 to the power 1 as m equals to 1 into 0.94, okay, so this is this gives 841.05 into 0.89 into 0.87 into 0.94, and this is 612.15 watt per meter square. So this is the S value which we got. Now we will calculate the useful heat gain rate, okay, that means QU. So the useful heat gain rate QU is given as FR WL S minus UL by C TFI minus TA, okay. So first we need to calculate this FR is the heat removal factor, and to calculate FR we also require F dash value. So the expression of F dash 1 by F dash equals to UL to 1 by UL plus B by N pi DIHF. You know, all these questions are easy questions. We just need to know the right formula, okay, and then we just need to put the values and we'll get the answer. These are the simple questions, okay. So putting all the values, so UL is given here, the overall loss coefficient 10.5 watt per meter square per Kelvin. And also while solving these questions, please make sure that the units are correct, because some are in centimeters, some are in millimeter, and some are in meters. So you need to be consistent, otherwise there will be a lot of different answers you will get, okay. So this is 10.5 to 1 by 10.5 plus 0.06, as B is 6 centimeters, so in meter it is 0.06, and then 2 into pi into, this is di, so di is given here 14 millimeter. Okay, so converting it into meter, it will be 0.0014. okay, sorry, not 10, 0.014, and HF is given as 230. So if you solve this, you will get 1 by f dash equals to 1.0311, and solving this you will get f dash equals to 0.9698. okay, so now we can calculate the heat to mole factor Fr, which is m dot Cp by BULL into 1 minus exponential of minus f dash BUL by L by m dot Cp. So first we need to calculate this expression, okay, this one. So m dot Cp by BUL into L, and so here if you see, m dot is given as 1.2 kilogram per minute. Okay, so we need to change the unit, so we will divide it by 60, 1.25 by 60 into Cp is 2350, it is given 2.35 kilojoule, so that means 2350 joule. Okay, divided by B 0.06, UL is given 10.5, L is 2, so if you solve this you will get 38.856. now we can put this value here, so Fr equals to 38.856. if you know, this is also the same expression, just the inverse, so it is 1 minus exponential of minus f dash we have calculated 0.9698 divided by 38.856. okay, so Fr is 0.9578. this is the heat to mole factor we got. So now we have all the values, so we can calculate the useful heat gain rate. Useful heat gain rate QU equals to, so Fr is 0.9578 into W we have calculated 0.39, L is given in 2, S we have calculated 612.15, UL is given 10.5, C is also given 7.5, TFI, that means input fluid temperature is given, it is 130 degree, and the ambient temperature is 21. okay, so if you solve this you will get QU equals to 325.78 watt. okay, so this is the useful heat gain. Now we can calculate the quantities. So first TFO, so from heat balance equation, okay, so this is m dot Cp delta T equals to QU. so again we have m dot, it is 1.25 kilogram per minute, so change it to per hour, so divided by 60 into Cp, that is 2350, and then delta T is, that means output temperature of fluid minus input temperature, and input is already given, it is 130, and this is equals to 325.78, which we have just calculated, QU. so if you solve this, TFO equals to 130 plus 325.78 into 60 divided by 1.25 into 2350. So TFO is 136.65 degrees centigrade. Okay, so this is the outlet temperature. So if you can see the increase in temperature is equals to 6.65 degrees centigrade. Okay, and now the next one is we need to calculate the instantaneous efficiency, that means eta. So eta I. So instantaneous efficiency is nothing but the useful heat gain, that means Q upon total energy incident. I think it is okay, I'll just write the value. So it is 320.578. This is useful heat gain. Now here the total radiation including beam as well as diffuse radiation falling on the absorber plate. Okay, so this is 570 IB into RB 1.4243, and here also ID into its factor, that is 1 plus cos beta by 2, which is 162 into 1 plus cos 40 degree, since beta is 40, divided by 2. Okay, so this is the total radiation on a tilted surface. This one is total radiation on tilted surface, and then the area of the entire collector, that means end up. So here W into L basically, so 0.39 into 2. So if you solve this, you will get eta is 0.4345, 0.4354. so that means eta equals to 43.54%, which is a very good efficiency. Okay, so this question was to calculate the outlet temperature of the fluid circulating in a CPC and the efficiency of the CPC. So we have calculated here. Okay, so first we have calculated the geometries and other factors which were not given. Then we calculated the useful flux hitting on the absorber of the CPC, and then we calculated the useful heat gain rate, and now we had all the things to calculate the required quantity, that means the TFO, outlet temperature of fluid, and eta I, that means instantaneous efficiency. Okay, so this is the last question for this session, and it is on central receiver tower. So just to remind you that we have, in this case we have heliostats placed on the ground, okay, in a different manner, and then we have a big tower here, receiver, and these heliostats were trapped. Okay, so that at always the beam radiation hitting to the surface is normal or parallel to the normal of the plane of the surface. Okay, that means they are coinciding, or that is why it is called heliostat. That means it is constantly tracking the sun, so that it is always facing towards the sun. Okay, so one thing is important, like how to place these heliostats in the ground. So there are different structures or the patterns in which we can place these heliostats, because it takes a large area, and we don't want that one heliostat shadows the another heliostat. Okay, so that either it blocks the incident radiation or it blocks the reflected radiation. Okay, so that is why there are studies to optimize the position of these heliostats in the field. And also we don't need and also like we need to compact these heliostats. So first our priority is to place it such that one heliostat cannot cover the other heliostat. Okay, and also we need to minimize the area as much as possible, otherwise it will increase the cost. So that is why there are a lot of patterns. If you search the research paper of optimization of these heliostat fields, you will get lot of papers where they have mentioned, or they have like generated the algorithm to place these heliostats. Okay, depending upon the constraint. That means it one heliostat shouldn't shade the other heliostat, or no, or neither it block the reflected radiation. Okay, because if I have two heliostats, these, so either first it shouldn't block the radiation hitting to the surface, and also it shouldn't block the radiation reflected by this heliostat towards the receiver. Okay, so yeah, you for the knowledge you can check some papers how to place these heliostats in the field. Okay, so so here let's come to question. The question is, a central receiver collector system consists of 1800 heliostats, each 6.5 meter into 6.5 meter in size. The height of the central tower is 80 meter and the rim angle is 81, sorry, it is 81 degree. Okay, it's not 810, so it is 81 degree. The size of the image at absorber is 6.5 meter. Calculate ground area around tower, that means calculate AG, and concentration ratio, that means C. Okay, so what are the things given? You have given number of heliostats 1800. Okay, and the area of each heliostat or mirror, I can say, is given, that means 6.5 meter into 6 meter. Okay, the height of the central tower is also given, it is 80 meter, and rim angle, here rim angle is the receiver's rim angle, it is given as 81 degree. Image at absorber is, the size of the image at absorber is 6.5 meter. So here size of image is equal to the absorber size or the receiver size. So you can say that diameter of the absorber is 6.5 meter. I can show you the design of the receiver. Okay, so it looks like this. So suppose it is so for the central receiver collector, these are 3D concentrators. Okay, so they have this point sources, that means the sources are spherical in shape. So so this is dp by 2. Here dp is the size of this receiver. Okay, and this angle is the rim angle phi r. Okay, so this is dp, so dp is 6.5, that means it is equal to the size of the image, because image will be at the receiver surface, so that means whatever the size of the image will be the size of the receiver. Okay, so we have to calculate the ground area, that means AG, and concentration ratio C. So so first we need to calculate the absorber area of the absorber plate. So since dp and phi r is given, there is a formula to calculate the absorber plate area, which is AP equals to pi by 2. This you can this formula is available, is given in the Sukhatme Naik book. Okay, you can check. So pi by 2 dp square 1 plus sine phi r minus cos phi r by 2. So if you put all the values, 3.14 by 2 into, so dp square is so this is dp 6.5 meter, so it is 6.5 meter square, 1 plus sine 81 degree minus cos 81 by 2. So if you solve this, you will get AP equals to 126.66 meter square. And now so now the formula is the relation between the total area of the of the heliostat and the area covered by these heliostats at ground is given as NAM equals to psi into G. This psi factor is generally 0.4, so here we are taking it as 0.4. Okay, so we can calculate AG, which is the total ground area, okay, around the tower covered by heliostats. It is NAM by psi, so it is 1806.56 divided by 0.4, so it is 1755 sub meter square. So see, this is this much amount of area. This is a very huge space, okay, and if we convert it into kilometer, it is 1.1755 kilometer square. Okay, so this is a lot of areas. Okay, so that is why we need to optimize the position of the heliostats in order to maximize the efficiency as well as minimize this AG. That is why there are a lot of research going on to in the optimization of heliostat field. Now the last one is to calculate the concentration ratio. So concentration ratio is nothing but the total area of collectors divided by total area of absorber or receiver. Total area of collector divided by total area of receiver. So total area of collector is nothing but N into AM, and total area of receiver, which is AP, and we have already calculated AP. So this is 1800 into 6.5 into 6 divided by 126.66. so the C is 554.24. this is a very high concentration. Okay, it goes to 1000 also, as if either we if we can decrease the absorber area, okay, then we can increase the concentration, but or we can increase the total area of collector, but again increasing the area of collector will impact on the cost, and also reducing the area of receiver will or may increase the losses such as spillage losses as well as radiation losses. Okay, so we need to optimize both field as well as receiver to get the maximum efficiency as well as minimum cost. So yeah, these are the three questions I had. So in this third question we have calculated the concentration ratio as well as ground area around tower for this central receiver tower system. In the second question we have analyzed the thermal performance of a CPC collector, and in the first question we have calculated the different geometry parameters of the CPC. Okay, so that's it for today's, and we will meet on next Friday. So from now on, thermal part, solar thermal and energy conversion part is over. Now we will have solar PV. That means solar radiation is directly converted into electricity. Now we don't require it in heat form, we can directly convert into electricity. Okay, that is for solar PV. Thank you very much.